In order to start this video off, we need to talk about what implicit functions actually are, and this is not an easy topic. I'm going to explain it the best way that I know how, but brace yourself because this is going to get abstract. If I give you 2 points in some sort of space, right? Something like this, and these points have no length, width, or height. They have no dimension. And I ask you to connect these 2 points with a line. There exists infinitely many ways to do this. You could think of a curved line like this, you could think of one like this, and you could imagine there's a million other options. But if I add the constraint that this line has to be straight, then all of those possibilities vanish and we are left with just one, something that looks like that. The resulting construct now, although still lacking in width and height, possesses length. And for a point on this line, there's only one way in which it can move. A more formal way of expressing this, which you may hear in fields like physics and engineering, is that a point on this line only has one translational degree of freedom, meaning a point on this line only has one parameter to describe its location, which can vary independently. One way to formalize this idea and define it in a way that allows us to subject it to analysis is to define a coordinate, for example, x, which represents how far along on the line we are. Of course, how far along as a concept completely falls apart when looking at points in isolation and only makes sense for points relative to one another. For example, the identity of your variable x-coordinate in this case is completely at the mercy of where you decide to place your 0 point, or the point 1, or 2, or pi. It doesn't matter what other point you pick actually, but you need 2 points in order to define some sort of quantity length, which represents the distance along this line between those 2 points. So let's just agree to set this point equal to 0. And we'll say that the coordinate which represents this is called x. So this is the point on the line x is equal to 0. Now, instantly and in one fell swoop, we have assigned an identity to an unimaginably infinite amount of points, lacking in any dimension but defined implicitly by the fact that they exist in the space defined by this line, and they can be identified by the distance between where they exist, so let's say example this point here, and some other point which we named 0. This distance we'll call x, and this would be the point x. Now I want you to notice the profundity of this. This simple act of naming 2 different points lacking in any dimension created an object with one dimension, seemingly out of nothing. This object consists of an infinite amount of these points which do not have length, width, or height. They are all nothing, yet somehow, some way, they come together in order to create something. Now here I've cleaned things up a little bit because we're going to introduce another line, and we're going to put it perpendicular to our original line, our x line. This line we're also going to give a name, and we're going to call it y by convention. And now, in a manner quite similar to the construction of a line with one dimension from 2 points lacking in any dimension, we have instantly created a space with 2 dimensions from 2 objects with 1 dimension. Points in this space can be identified by their distance from the point 0 along the line we called x, and their distance from the point 0 along the line that we called y. Now we are in familiar territory, but we have this idea now that we are viewing things dimensionally. In this 2-dimensional space, x and y have no relationship to one another. Points can and indeed do exist literally everywhere in this space, and each and every one of them has a specific and unique identifier, an xy pair, armed with which we can locate seamlessly and instantaneously. However, we can put restrictions on this. I can, for example, impose some sort of one-dimensional curve onto this space and make the declaration that I am only concerned with the points that exist on said curve. So let's draw something. This is going to have 1 dimension. It's just a line. And now I'm only concerned with points that rest on that curve. Let's say it goes on forever. Now notice in doing so, I have implicitly declared that x and y are no longer independent of one another. An easy way to understand this is to think if I'm given an x value of some point on this curve, like let's look for example at this x value, I know that exactly where the y value is going to be, because I can look up to this curve and see that it's going to be this value right here. So now that I've restricted the domain of this to just this one-dimensional curve in this two-dimensional space, I have implicitly defined a relationship between these two variables which make up this space. And now if I give you an x value, you can instantly tell me exactly what the y value is which corresponds to it on the curve. Now I want you to notice that if I draw some sort of two-dimensional object onto this space, for example a square like this, and I declare that I'm only concerned with points which exist in said two-dimensional region, I have not implied some sort of relationship between x and y. If I tell you what value of x a point has in this region, for example, although the value of y indeed has bounds defined by the edges of this region we are concerned with, there are still infinitely many points which exist in the region that have that specified value of x. For example, if I say that the point in question has this as its x value, there are still infinitely many points along this line that is bounded that could satisfy this condition. So x and y are still independent when we're only concerning ourselves with a two-dimensional subsection. And so this implied relationship between the two variables, each representing proximity to some point, is precipitated by a literal dimensional collapse that brings us down from 2 dimensions to 1. With the declaration that we are no longer concerned with the collection of all points in this two-dimensional space with length and width, or even a subspace, a two-dimensional subspace, but rather only those on some curve, lacking in width and height, but possessing a length, comes an implicit relationship between our two parameters, x and y. Understanding the concept of a classical implicit function involves extending this idea to a three-dimensional space, wherein we will see our first glimpses of functions of several variables and multivariable calculus. So imagine we declare some third number line, z, but we keep in convention and we put it normal to our x and y plane. So here I'm going to have my x and y plane. I'm just going to draw it like this because z is going to represent height, for example. And so we'll have something like this. We have our y-axis, our x-axis, and our z-axis. This would be negative x, negative y, and negative z. With the simple addition of this third line, lacking in width and height but possessing length, we have instantly created a three-dimensional space wherein there are infinitely many points that can all be identified by their proximity to some reference point along the three axes. In that case, we generally call that the origin, where all three of these are equal to 0. Similarly, every single point in this three-dimensional space can be identified by this coordinate pair of x, y, and z coordinates. Here, x, y, and z are completely independent of one another, as there are points which exist for every possible permutation of x, y, and z within this space. But let's see what happens when we restrict our domain to just the points which satisfy the conditions z is equal to x squared plus y squared minus 1. So this might look intimidating at first, but what will happen when x and y are equal to 0? Well, z would just be equal to negative 1, so we can plot that on this point. It would be something like this. And now we can think, what happens when z is equal to 0 and x is equal to 1, and y would be equal to 0 then, because we would have 0 is equal to 1 minus 1 plus y squared is equal to 0, y must be equal to 0. And so when z is equal to 0 and x is equal to 0, y must be equal to 1. And the same reasoning will allow us to conclude that the same is true for the points z is equal to 0, y is equal to 0, x is equal to 1, negative 1, and y is equal to negative 1. And so we have this little shape here. Now, what's going to happen when we say that x is equal to 0, and that's it? We will be left with z is equal to y squared minus 1. And if I was to write y is equal to x squared minus 1, it would be pretty easy for you to plot this. This is just a parabola. So this z is equal to y squared minus 1 is just a parabola opening up with a vertex at 0, negative 1 in the zy plane, which would be this plane here. And so we can just plot that. We can plot our parabola opening up from that vertex in the zy plane, and it would look something like this. And then here we could do the same thing with x. What happens when y is equal to 0? We would get that z is equal to x squared minus 1 when y is equal to 0. And I'll put the same condition here when x is equal to 0. And so we get these parabolic cross sections here. And we would get some figure that looks like this, like a bowl opening upwards. By concerning myself only with the points in this three-dimensional space which satisfy this relationship here, this equation, I have collapsed the dimension, creating a surface in the three-dimensional space that is completely flat. Points along its surface have 2 degrees of freedom. They could move to their left or right, so to speak. They could move up or down, or maybe north and south is a better way to think of it in this context. But as long as they are restricted to be on the surface, we have created those are the only 2 options that they have. So this is a 2-dimensional surface. Notice here that in collapsing a dimension, we have implied a relationship between z, x, and y, but let us exercise caution. If I give you a value for x and a value for y, then you could very quickly and easily identify exactly what the value of z would be, and that's just simple algebra. But if I gave you a value for x, for example, and that was it, there would still be infinitely many points to choose from. In this way, z is dependent on x and y, x is dependent on y and z, and y is dependent on z and x, but the 3 variables are, at the same time, independent of one another. Is that confusing? Probably, but let's not depart from this idea quite yet, and let's instead focus in on this idea of giving a value for x, which we actually already did when we were plotting this function here, when we said when x is equal to 0. What's really going on here is that when I give you a value of x, there is a dimensional collapse here, and now we are no longer concerned with this entire 3-dimensional boundless volume, but instead we are concerned with this boundless 2-dimensional plane. In this case, we were dealing with the points where x was equal to 0, so that was this zy plane here. But it didn't have to be that. It could be all the points where x was equal to 5, and so that would be this plane here. It would look something like this, although I'm very bad at drawing. And what happens is when I add that additional constraint from the beginning, our equation here, there's another dimensional collapse. And so now we are down from 3 dimensions to 1 dimension, and we're represented, that can be represented by not a plane, but a curve in the plane. And indeed, that would be this one here, the curve in the zy plane that is a cross-section of our 2-dimensional surface given by this equation z is equal to x squared plus y squared minus 1. An implicit function, then, is one in which a relationship between some variables is implied as a result of one of these dimensional collapses. Let's go back to our equation and see what happens when we add the restriction that z is equal to 0. Visually speaking, we would be taking a cross-section of our surface in this 3-dimensional space, but only in the xy plane here. And so that would look something like this. It looks pretty circular. Maybe I should do this in a different color because it's getting messy now. So this is going to be our cross-section where z is equal to 0. It would be this little figure here. Now, algebraically, if we go back to our equation, what this is actually given by is 0 for z is equal to x squared plus y squared minus 1. And another way to write this would be that x squared plus y squared would be equal to 1. And the astute observer might recognize some similarities here with the Pythagorean theorem or the distance theorem, which is really just an application of Pythagorean theorem. But if you think about this, this is really just going to give a collection of all the points in the xy plane that are exactly 1 unit away from the center, 0 here. And so what this is a circle of a radius 1 centered at the origin. That's what this equation here is. So in collapsing a dimension of this higher level function and taking a cross-section of it, we have implicitly defined a relationship between x and y, because now the value of x that I get is going to depend on what value of y I put in, and vice versa. For example, if I tell you that my value of x is going to be 0, we know that y must be equal to 1 or negative 1. If I tell you that y is equal to 0, x must be equal to 1 or negative 1. Visually, you could think if I tell you that x is equal to 0, that would be the points along this line here, and you could see that that's going to be where y is equal to 1 and where y is equal to negative 1. So functions defined in this way as a result of a dimensional collapse of one of these higher level functions are known as implicit functions, where a relationship between the leftover variables, in this case x and y, is implied. That did not exist before, where x, y, and z were independent of one another. Most of the ordinary equations that we're used to are with a y on the left hand side and a bunch of x terms and operators on the right are generally known as explicit functions. But what makes this idea so hard to understand, at least for me, is that in general most of these implicit functions can be written in explicit terms. For instance, let's take our circle equation and let's try to solve for y. We would get that y squared is equal to 1 minus x squared, and then we just take the square root. Y would be equal to the positive and negative square root of 1 minus x squared. And so you could think of this as two different functions. Maybe you would have y is equal to the square root of 1 minus x squared, and y is equal to the negative square root of 1 minus x squared. And if you plot both of those onto a graph, you would be left with a circle. And generally, I've found that this tends to hold true for most functions that are known as implicit functions. For example, in doing research for this video, I came across this core article that asked the question, what's the difference between an implicit and explicit function? And they said that the difference is that in an implicit function, x and y cannot be separated. And the example that they gave was that it was this equation. It was x squared plus 2xy plus y squared was equal to 0. And they said this is implicit because x and y cannot be separated. But this is literally just the same thing as x plus y squared is equal to 0, and if you take the square root of 0, it's just 0, and so this is just saying y is equal to negative x. They definitely can be separated. And so what this is this is the cross-section of a three-dimensional surface given by this equation, where you would say z is equal to this, but it's the cross-section where z was equal to 0, and what that would look like is a line with a slope of negative 1, y is equal to negative x. That's what you would be left with. And so this difference here is hard to understand. The best I can offer as an answer to this problem is that I imagine that there are probably functions wherein a relationship between x and y is implied, but the variables are impossible to separate. But that doesn't matter. There are cases where it's likely easier to separate the variables, creating an explicit function, so to speak, but there are also cases where it is not easier to separate the variables. For example, I would argue that this format is a lot preferable to this one for our equation of a circle. When you're dealing with separated variables, you're dealing with an explicit form, and wherein one variable is written explicitly in the terms of the other, but when the variables are not separated, you're dealing with an implicit form. But all functions are implicit. There's no such thing as a dependent or independent variable in mathematics. A relationship is just that, a relationship. I want to reiterate that because I think it's important. All functions are implicit. A function is a dimensional collapse, which implies a relationship between the variables which make up the space inside which it resides. Just as a line in two-dimensional space is a one-dimensional construction, restricting the domain of possible values in such a way that a relationship between the variables which compose that xy plane is implied. All functions can be thought of in this way, and indeed, that is what they are under the hood of mathematics, so to speak. Sometimes we get lucky, and it's very easy to write out a specific function algebraically, and sometimes we don't. But this is what they are. So hopefully that brought a little bit of understanding as to what an implicit function actually is. But now let's look at a technique called implicit differentiation, which takes functions that are written in this form implicitly and allows us to take derivatives of them. And this is really, in essence, is just a neat application of the chain rule. And I'll give a little example of that. Let's take our implicit equation from earlier, the one for a circle with a radius of 1 centered about the origin. We have x squared plus y squared is equal to 1. And let's try to differentiate this equation with respect to x. So we want to know how y changes with respect to x. So we could start by differentiating both sides. Just simple algebra, if this is equal to this, then taking the derivatives of both sides, they should be equal. And so we could take the derivative of the left side here, and I'm just going to break this up into the derivatives of both of these. Here we go. Take the derivative of y squared. And then we'll take the derivative of the right side, but this is just a constant. And so how we change x is not going to affect this constant at all. And so we could just say that this derivative is equal to 0. And then we have the ability to do this very easily. We know how to take the derivative of x squared with respect to x. That's just equal to 2x. And then this is the only part where things get a little bit interesting. We're asked to take the derivative of y squared with respect to x. Now, on impulse, you might think, well, y is not x. Like, it's a variable that doesn't depend on x, and so the derivative of this with respect to x is just equal to 0, almost similar to a constant. As we change x, y isn't going to change because it's a different variable. But remember, there is an implicit relationship between these two variables. And indeed, if we rewrote this equation in terms of y, we could write this as y is equal to the positive and negative square root of 1 minus x squared. And so it's very obvious when you write it this way that as you change the values of x, the values of y are going to change. And another way to say that is that y in this case is really a function of x. And this isn't written explicitly, but here it's implied that y is a function of x. And so we have some function of x being squared, and we have the ability to negotiate situations where that happens. You could think of this as a situation where we have f of g of x here. Or maybe I'll make it a little bit more obvious. I'll write it as f of y of x, where f of x is equal to x squared. This is literally just an application of the chain rule. And so this is all implicit differentiation is. We're just applying the chain rule here. So first we'll differentiate this with respect to y. We know how to do that. That's just 2y. It's the same as taking this derivative over here. So we'll do 2y. And then we need to take the derivative of the inside function, which is this. It's y. But because we don't know what the derivative of that function is, we could just write it as the derivative of y with respect to x. And this is all equal to 0. And now that all this differentiation is done, we can just solve for the derivative algebraically. And so we would subtract x from both sides and divide by 2y, and we get that the derivative of y with respect to x is equal to negative x over y. And so if I give you some points on the circle, for example, if I gave you the point on this circle, square root of 2 over 2, square root of 2 over 2, you would very quickly be able to tell me that the slope of a line tangent to the circle at that point would be equal to negative 1, right? And we could actually do the same thing here. We could differentiate this explicitly. This is another application of the chain rule. So the derivative with y with respect to x here, the thing is that you would have to break this up into a positive and negative component. So I'll just do the positive component, and the negative component would be the same process. You would just have to use negative constant up front. So we'll just differentiate the positive component to show it can be done. This is just the square root, so this is going to be 1 over 2 times the square root applied at that function, 1 minus x squared, and then we multiply by the derivative of the inside function. The derivative of this inside component here is just going to be negative 2x. Negative 2x. These 2's are going to cancel, and we get that dy dx is equal to negative x over square root of 1 minus x squared. Now, at first, these two expressions look different, but they are not different. And the reason for that is because if you look up here, this is what y is equal to, and if you just plug that into this implicit equation here, you will get our original equation. So we do see agreement between these two. I have a bunch of different examples here, example problems, where we can use implicit differentiation in order to get some practice, but also to expand our general knowledge of calculus. But I think this video has already gotten pretty long with my explanation of implicit functions and implicit differentiation. So I'm going to break this off into a separate video that's just full of examples and example problems. So if y'all are interested in that, just check it out. It should be the next video in the playlist. But thank you guys for watching. I'll see you in the next one.